All right, in the last chapter, we were talking about gases, right? Gases are extremely spread out particles that we don't get interactions between the particles, and we can ignore the size of the particles compared to the space they occupy. All of those things. Well, this topic is about liquids and solids. So, as opposed to gases that are really have far distances between the particles, liquids and solids, the particles are closer, more packed together. Um, with a liquid, you're allowed a kind of a free sliding motion past the particles, whereas with a solid, the particles are locked into a position. So you've got the three halogens, right? Chlorine at room temperature exists as a gas, bromine exists as a liquid, iodine exists as a solid. So I guess the question is why? Why more packed together with iodine? So you've got very low density with gases, higher density with liquids and solids. Gases are compressible, whereas liquids and solids basically are not. And like I said, there's no you're allowed any kind of motion you want with a gas. Gas particles are not hindered from going any particular direction, whereas liquids, because they're being held together, are um, are held to each other. They're allowed kind of a sliding motion past each other, whereas solids, the only thing you're allowed is kind of a vibration, right? You're locked into a position, but you're allowed to vibrate. States of matter: solid, liquid, and gas. Various states of matter can be understood by examining the attractive forces between the molecules. So this is the why. If you can hear that, that's my new dog. My old dog doesn't interact anymore. My new dog does. All right, moving on. So why do things liquefy and solidify? It's because of intermolecular forces. All right, so we know something about this, right? We can draw Lewis dot structures, make a prediction as to whether they're polar or not. If you're an ionic compound, right, you've got a cation and an anion. You've got what's called an ion-ion attraction between the particles in the solid. All right, that's what holds ionic compounds together. All right, and as we know, ionic compounds are very hard to melt. I mean, you get salt up to something like 2,000 degrees Celsius if you wanted to melt it. So these are strong attractions. Ion dipole, all right, that's when you've got a cation or an anion surrounded by something that's polar, like any kind of aqueous solution. Ion-induced dipole, well, that would be a cation or an anion with something nonpolar. Dipole-dipole is when two polar things interact with each other. Dipole-induced dipole would be the interaction between a polar thing and a nonpolar thing. And induced dipole attractive forces. That's when you're nonpolar. This is the only option you're left with when you have something like methane. Why would methane liquefy? Well, first of all, you got to get really, really cold because these induced dipole attractions between the two nonpolar methanes are really weak. So weak attractions with induced dipole. Anytime you have anything other than ion in it, it falls under this heading called van der Waals forces. So dipole-induced induced dipole. These are all examples of van der Waals forces. So as we just said, ion-ion attraction is the basis behind ionic bonding. So covalent ionic crystals, very hard to pull apart. So this is a very strong attraction. And we already know, right? The more charged the particle, the smaller the particle, the greater this attraction between the particles. Then there's ion dipole attractive forces. All right, so something like sodium chloride dissolving in water, right? You've got the dipole of water, right? A negative side and a positive side interacting with the cation or the anion. So you've got the positive side of water surrounding the anion. You've got the negative side of water surrounding the cation. Dipole. Well, this is meaning a rationalization as to why polar things liquefy. So if I get something like, oh, what is this? You got a cyanogen group on methane, cyanomethane. You've got this negative side to the particle and a positive side of the particle. So the negative side and the particle side of each of these particles, right? These little look like little worms here, are lining up in such a way to maximize the attraction between the negative end of the molecule and the positive side of another molecule. So this is a rationale as to why these things liquefy. So again, you don't want to line up in such a way where you get repulsive forces, right? So this would be, they have blue lines for repulsive situations and red lines for attractive situations. So liquefying, solidifying, it's all about the attractive forces between the particles. All right, hydrogen bonding is this special type of dipole-dipole interaction. All right, so it's a super strong dipole-dipole interaction. And anytime you have an OH group, an NH group, or an FH group, you get this super strong kind of dipole-dipole interaction. So I don't know, a lot of people get confused by this because of the word bond. There's no bond here. This is just a attraction between the water molecule and the other water molecule, or the hydrogen fluoride molecule and the other hydrogen fluoride molecule. So you get the hydrogen of the one molecule lining up with the oxygen or the fluorine of the other molecule, and this is what causes them to liquefy. So the negative side of water lines up with the positive side of water. This special kind of dipole-dipole interaction is called hydrogen bonding. Yeah, another picture of it. So the hydrogen bond is just the attraction between the negative side of the one water molecule and the positive side of the other water molecule. It has a profound effect, right? So if you're looking at two molecules, this is propane and this is ethanol, they're about the same mass. So if you're talking about what makes something easy to boil or not, part of it is its weight. If you're a heavy particle, you're harder to put into the gas phase than if you're a lighter particle. So these particles are about the same. Propane, as we know, exists as a gas at 25 degrees Celsius, whereas ethanol does not. And the reason for this is one is capable of hydrogen bonding, one isn't. So with ethanol, its boiling point is up at about 78 degrees Celsius, whereas propane, if you want to boil it, you only got to get the temperature up to minus 42 degrees Celsius. So, again, a tribute to how strong this special kind of dipole-dipole interaction is. All right, so what are we doing here? I guess we're comparing elements going on. Oh, I need a periodic table in front of me. What are we looking at? Oh, here we go. Found one. So periodic table, we're looking at going down group 4A, carbon, silicon, germanium, tin. So we're connecting 4 hydrogens up to each of the central atoms. And what we're basically tracking here is the boiling point. So as you go down the group 4A, the atoms get heavier and heavier, right? Silicon's heavier than germanium, germanium's heavier than, silicon is heavier than carbon, germanium is heavier than silicon, and so on. So the heavier the particle, the harder it is to boil. If you do the same thing going down group 6A, where you've got oxygen, sulfur, selenium, and beryllium, you see that all of a sudden you're going against the trend because of this hydrogen bonding between the waters. You get a way higher boiling point for its mass with water than you do with dihydrogen sulfide or dihydrogen selenide or dihydrogen pterylide. These are, even though they're more massive, they're not capable of hydrogen bonding. So anything with an NH group or an OH group is capable of this special kind of dipole-dipole. The only thing that has an FH group is hydrogen fluoride. So hydrogen fluoride also considered hydrogen bonding. You get hydrogen bonding in the DNA strand, right? This is the rungs of the ladder in the DNA strand. So you get the hydrogen of the one molecule lining up with the oxygen of the nitrogen of the other molecule, and this attraction between thymine and adenine is the thing that holds the two strands of the DNA molecule together. Same with guanine and cytosine. So with adenine and thymine, you're only capable of two hydrogen bonding interactions, whereas with guanine and cytosine, you get three. So more guanine and cytosine in a particular segment of DNA means it's going to be hard to pull that segment apart. All right, dispersion forces is another word for induced dipole attractions. So we get these temporary dipoles. So yeah, what is an induced dipole? How do you induce a dipole? Well, this is how it works. If I take something that's charged, like a cation, and put it next to another object, what I can do is temporarily shift the electrons over towards one side. Right? The electrons will be attracted to the cation, and the electrons get shifted. The cloud, right, gets warped over towards the positive side, and you get a temporary situation. As long as the positive's there, you'll get this attraction between the nonpolar thing or the thing that I'm inducing a dipole in and the plus charge. So this is what's called an induced dipole attraction. The term polarizability refers to how easy it is to induce this dipole, how easy it's to shift that electron cloud so that you get this tug between the nonpolar thing and the cation. Polarizability increases with the size of the atom, so big puffy atoms are easier to warp than small tight atoms. All right, another word for it is hard, right? So fluorine's a tight cloud, a hard cloud, hard to polarize. Whereas iodine, right, as you go down the group, you're getting more and more shielding, right? Those outer electrons are being held looser, so they're more easy to warp. So there's your explanation as to why iodine comes as a solid at room temperature and chlorine comes as a gas. It's easier to polarize iodine and get this tug between the nonpolar I2s and the F2s. Dipole-induced dipole. So if we can induce a dipole with a cation or an anion, we can induce a dipole with something that's polar, right? So if there's a positive side and a negative side to a molecule, you can shift the electrons over to the one side, attract it towards the positive side of the molecule, and it can induce a dipole. So dipole-induced dipole. So this would be like the attraction between oil and water, right? Water is a polar molecule. Oil is not, right? Oil is a long hydrocarbon that's not polar. So the attraction between water and oil would be a dipole-induced dipole attraction. All right, the weird one is induced dipole. So just how does this happen? Well, happens by just random motion. The way you visualize this is just by random motion of the electrons. The electrons end up more on one side of the cloud than another. So just for that temporary moment, you get a dipole. Now you get an attraction between the electrons in the other cloud, and you induce a dipole in the other one. So you get an attraction between the two. So again, just by random motion of the electrons, right? So London dispersion forces, right? Induced dipole, you're going to get random motion of the electrons. You temporarily induce a dipole, and that can cause the other atom to get an induced dipole, and we get an attraction between the two. So you might be saying to yourself, well, Jesus, this seems like, kind of far-fetched, right? Well, hey, it's an explanation. Why? Why would something like nitrogen, non-polar, liquefy to turn into liquid nitrogen? And the answer is just by random motion, we get the electrons on the one side of the nitrogen molecule, and that can induce a dipole in another nitrogen, and this tug between the two can be the reason why they liquefy. So there's always London forces or this induced dipole. anytime you have a polar molecule, nonpolar molecule, you have this warping of electron clouds. You have this tug between the molecules. So big long molecules where the molecules are allowed to line up close to each other, you get a greater induced dipole effect than you do with fat branched molecules, right, where the atoms aren't allowed to get as close to each other and induce a dipole. So with something like N-pentene, same mass as neopentane. One is branched, one isn't. One, the molecules can get closer and induce a dipole. Strength of dispersion forces tends to increase with molecular weight. So again, the bigger the atom, the easier it is to induce a dipole. If one molecule is much larger than another, dispersion forces is most likely the reason why it liquefies. All right, so big long molecules or bigger molecules, you get a greater cumulative effect of dispersion forces than you do with short, small molecules. When you have small molecules, then it's a question of whether you have a dipole or not. Right, so if you've got an OH group or an NH group, that's going to be the main reason why you're going to get an attraction between the particles and get liquefaction. So here they all are laid out in terms of the interactions, right? Starting with ion-ion, ending with induced dipole, and they give you some sort of indication as to how strong these are, right? So the weakest interaction is induced dipole. The strongest interaction is ion-ion. Notice hydrogen bonding would be at the high end of dipole-dipole, right? So up around 25 kilojoules per mole in terms of breaking waters apart. So again, hydrogen bonding is just a special kind of dipole-dipole.